So in addition to completing the work from Tuesday, Wednesday, which I hope you did. I'm not checking on it, but I hope you did do that. And of course, ask questions if you have anything you weren't too sure about. I also asked you to have a look at this post. I'm going to go through it fairly quickly. Feel free to stop me if you are not too sure what's going on. But honestly, I did ask you to do this so that we could move fairly quickly through this. So if I'm bogged down by people who just haven't watched it, didn't try it themselves, if you're lost, that is why. Watch the video over and over again until you get it, I suppose. So basically, I want you to remember that sine, cosine, and tangent are fundamentally defined as a ratio between two sides of a right angle triangle. And then all of our work has been, since then, extending our definition of this ratio to coordinates in the unit circle. So it takes the coordinates of the unit circle as in the first quadrant, which is where the angle is acute, and then it extends it so the angle can be obtuse, reflex, above 360, and so on. Okay, so we've extended our understanding. Once we've extended our understanding, then we can start treating sine, cosine, and tan as functions. So we've got this idea, really, where we've got this trig function, and in goes an angle measurement, and out comes a ratio, but that only works for right angle triangles. So eventually we worked out that it's kind of like coordinates or the gradient using that unit circle kind of definition stuff. Okay, so we get a value out of it. We don't get an angle out of it, we get a value out of it, some sort of fraction. And based upon how this ratio works, tells us something about these functions. Okay, or how we treat them as a function. So input is angle, output is ratio. And I asked you to consider the domain of sine and cosine. What are legitimate input values? Okay, so what kind of values? Sometimes remember what I said to you before about looking at domain. Sometimes looking at the opposite is useful, like what doesn't count. So is there any value that would not count as an input to sine or cosine? Not now. Everything works, doesn't it? So if I just work in degrees only to give you a sense of that, whether I put in minus 360, positive 360, 0, 1.2, even pi degrees, any possible value I want to consider, I can input into sine and cosine, and it will output that ratio thing. Okay? So if I look at the domain of sine and or cosine, I know you can't see, it's because I was just getting a start there. Domain of sine or cosine, then the input would be basically this, anything. And that's whether it's in degrees or in radians. Any old value goes in and any old value goes out. The key for radians versus degrees is really simply what your calculator is in, because if your calculator is in radians mode, then it's expecting its input to be a radian angle. If your calculator is in degrees mode, it's expecting a degree angle as its input. So the function actually changes its output based upon what mode your calculator's in. So just be mindful of that. It's perfectly legitimate away from the calculator to simply state this is radians or this is degrees, and then sine or cosine or tan will work from there. So that's the domain. What about the range? The range is the outputs, isn't it? The range is the outputs, the range of outputs. Now, if we think about the right angle trig, then we are always going from opposite or adjacent over hypotenuse, and hypotenuse is the longest side. So therefore, opposite over hypotenuse and adjacent over hypotenuse is always less than 1. That's for right angle trig. So I'm going to put theta hat on that right-angled trig. You with me so far? Beyond the right-angled trig, we have the same, remember, the same values, but it's just that the values can be negative as well. Okay? So beyond the right-angled trig, we have theta, or in this case, I'll call it it shouldn't be theta anyway. Y must be between 1 and -1. The range of the sine and cosine function must be between 1 and -1. But there's one other thing we need to consider, and that's the boundary values. And if you remember, if I can just quickly flick back to that. If you remember that at the boundaries, sine and cosine are either 1 or 0 or -1 or 0. Okay? So 0 and 1 and -1 are also included in the range. They are also possible outputs. So when I do that, I end up with that. That's the range of sine and cosine. Y is between -1 and 1, or if you like, y is between square brackets this time. Y is between -1 and 1. Now that's big brain moments there. Just checking to see if anyone's got any questions on that. Okay, so the function is going to be between -1 and 1 as its output, and we're going to input basically anything we want to. All right, that's that. Then I asked you to consider tangent. And I gave you a prompt here as well. Are there any invalued values that we can, for the domain, i.e., are there any inputs that don't work? If you've thought about it before, you probably have an answer here if you've done your homework. Anyone come up with an answer for that one? Okay, either you didn't do your homework or you couldn't figure it out. If you remember from our work, I know you can't see it yet, I'm just priming. Tan worked everywhere except here and here, etc. Okay, so when there was a rise of 1 over a run of 0, that does not exist. You cannot have 1 divided by 0 or -1 divided by 0 either. Okay, so for 90 degrees or pi on 2 or 270 degrees, which is 3 pi on 2, tan does not exist. Okay, so that means I cannot input 90 degrees, I cannot input 270 degrees, and so on. Okay, so that means that the domain of tangent is between -infinity and infinity, but x does not equal pi on 2, 3 pi on 2, 5 pi on 2. Can you see how like the top number is just an odd number? 1, 3, 5. So we're adding a bit each time, adding pi each time. Oops. Etc. So x, there is a hole in our graph at each of those little steps there. Okay, and what about the range of tan? For sine and cosine, we were limited by -1 and 1. What are we limited with for tangent? Sorry? You can even have a run of 0, because that would be no rise over any run. That 0 divided by something is fine. So even 0 works. So as we get closer to 90 degrees, which is straight up and down, it's getting really, 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 really steep. So it's still legitimate. So we end up with the slope or the gradient being anything at all apart from, no, anything including 0. So the range for tangent is -infinity to infinity. The domain is limited, but the range is not. As it gets closer to these points here, though, where it's vertical, where it doesn't exist, it's just getting really, 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 really steep. And so it just climbs to infinity. Climbs to infinity just before here and after. Climbs to infinity before here and after. And so on. Might be negative infinity, but it's really, really steep. Negative infinity would be steep but downways, and positive infinity would be steep and upways. Alrighty? I hope that kind of makes sense to you. Then I asked you to consider looking at the links attached to this. And we'll do this really briefly. So what we saw, I can just zoom this one. And because it's International Radians Day, I'll put it into radians. What we saw is that we're going to start here at 0. So when the input is 0 radians, the output is the sine of 0 is just 0, so that's fine. In the first quadrant, these are just right angles. So let me go as far as the first quadrant. It draws this up to here. So it goes from 0 up to 1. Then in this quadrant, sine is still positive, but now the value of sine is going to reduce. So it goes from 1 back to 0. And so we get this happening. Yeah? So we've got it scribing down like that. In the third quadrant, sine is negative, and as we would expect, it would therefore drop below because the output is going to be negative. Remember, this is the input, this is the output. This is x, this is sine of x or y. So between here and here, it's actually going to be the same values as this, except negative. It's a reflection, effectively. So we get that. So that is a reflection of that. And then finally, we go back to the start again. This is a reflection of that. Okay, a diagonal reflection. Like that. Yeah? Of course I can. Now that we've got back to the 0 again, we know that angles beyond 360 will just ultimately continue the same pattern. And we have this beautiful sinusoidal wave. And you can see here that it's gone around like a little snail. So of course I can keep going around, but the function doesn't change. It's just a repeat of the function. Yeah? Now we're up to 41 pi on 2, or 41 pi on 2, or 41 over 2 pi. So that's like 3,690 degrees. It's just a repeat of the pattern over and over and over again. It repeats how often? Can't do a heat reset. It repeats every 360 degrees. It repeats every 2 pi. So if you look at that, 2 pi there it stops. And then if I keep going, up to 4 pi, now it's repeated again. And it repeats again. And it repeats again. So it's repeating every 2 pi. Backwards as well. Let's rewind it. And back we go. because we know that for sine and cosine, and tan as well, for the trig functions, basically there's an input which is positive, negative, big or small. All we're doing is we're working out which quadrant does it land in and then what the value is. The value here, 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 and here is the same. It's just positive or negative. And hence we have this beautiful sinusoidal pattern or shape, it's called. Sinusoidal is the absolute right word to use. Oops. How do I get out of this? This one, I guess. Without belaboring it, cosine's the same, except that with cosine, I have to go back, don't I? With cosine, our starting value is different. And if you have a look at the graphs, you'll see why. So going back to the start again here, at the start of cosine, we have it starting at 1 because of the x-axis thing. Remember, cosine is the x-coordinate, and it starts 1 unit away from 0. So at 0, the cosine is 1. And as we move into up for the first 90 degrees, these are all the acute angles, it's reducing, the ratio is reducing. Okay, so it's going down until it hits 90 degrees, where cosine is 0, and then it reflects across here. Cosine is negative, of course, in the second quadrant, which is why it's negative there. Cosine continues to be negative, but the value is increasing, which is why it's going back up to the x-axis. And then cosine continues here as well in the positive element, because cos is positive here. Yes, Sam?
Did you make this thing?
No, goodness me, I'm not that clever. And then as I rotate round, but thanks for thinking I did, though. I'll take that as my win for the day. We're rotating around. What do you notice about this shape compared to the sine shape? If you say nothing at all because they look exactly the same, you'll be right. They are the same shape. It's a sinusoidal shape as well, and backwards as well. And when I'm doing this kind of thing, you can't really tell. Oh, I've got to rewind it now. You can't really tell whether it's sine or cosine. And that's because of that special relationship I showed you in that right-angled triangle where sine and cosine are complementary to each other. In fact, the cosine graph, if we just don't worry about the values here, the cosine graph is just a sine graph shifted backwards or forwards by 90 degrees. It's the same function, just shifted one left or right. It's a translation, if you remember that from our other function work. Okay, so that's sine and cosine and how it looks as a function. And then the last one is tan, which does look completely different. And I will trace it because I think the trace does help you sort of see what's going on. I'll go to radians because I want you to try and focus on that. So the tan of 0 is 0, so it starts there, right? As it moves up to pi on 2, remember what that means. It means that the gradient, you can actually visually see this in the line here. The gradient is getting steeper and steeper and steeper and steeper and really steep. Have a look at the value of tan here. The gradient is 3.3. Tan is 3.3. A little bit further up, tan is 8.24. A little bit further up, so steep, 16.43. And I can keep making it steeper and steeper. It's off the charts now, but it says 24.5. And then really close, 48, 92, 1,255. It's just getting steeper and steeper and steeper. That was just before 90 degrees, etc. So it just continues to get steep. So you've got this lovely steep curve happening here. And then at 90 degrees, it's a dead zone. Now, I don't think we've done asymptotes yet, have we? If you did Maths Extended last year, you'll know what an asymptote is. An asymptote is a horizontal or vertical line that the function goes towards but never actually reaches. So in the case of tan, there's a vertical asymptote at x equals pi on 2. Okay, that line there is an asymptote. The graph never reaches it, but it keeps on moving closer and closer to it as it goes towards infinity. On the other side, there's that, so that red line represents it. When I'm on the other side, tan starts off really steep, but it also starts off really negative. So it starts off at negative infinity and starts getting flatter. So we get this happening between pi on 2 and pi. So very steep, flatter, 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 until we get to pi. Okay? Once we get to pi, we've hit 0 again. In this quadrant, CAST, okay, the turtles are over here. The sad turtles are over here. So tan is positive. So again, we have a positive, fairly flat gradient just off to the side here. And as I move towards the next axis line, we're getting steeper and steeper and steeper again. And so we end up growing the graph like so. It's getting steeper and steeper. And then it hits 270 degrees, 3 pi on 2. Again, it's an asymptote. Bang. And then the journey continues again, and so on. Okay? So, okay, just for Hunter, I'll just do this. Yes, good question. Marissa said, do we draw in the asymptotes? Yes, you do. I'll do this on the whiteboard. Sorry if you're watching this back on video. But what you'll do is you'll go like this, draw a dotted line in, and then do this, draw a dotted line in, and so on. Or, alternatively, you can do this, where you draw the dotted lines in first, and then notice how I'm not drawing the full slopey thing, just like I do with cubics. I just do one half of it first and then the other half. I think it makes for a nicer slope, a nicer graph in the end. Sorry if you're watching this back on video. Okay, so question. How long is it before the graph repeats? For sine and cosine, it was 2 pi, or 360 degrees. What is it for tan? Not quite. I understand why you're saying that, though.
1 pi.
It's 1 pi, yeah. So the actual repetition, if I start from 0 here, to work out how the repetition, what we're doing is we're saying, here it is at 0. When does it get back to 0 again and repeat the pattern? So here, 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 it's now back to 0, and this pattern is the pattern that repeats itself. Okay? Here, asymptote, here to 2 pi, to 2 pi and beyond. Okay? So here to here is the repeat. Now, when we talk about repetition, I'm starting from 0, but it doesn't matter where I start. If you look at, we talk about it as the length. In other words, if I start here at this asymptote, how long is it before I get to my next asymptote? Well, that length there is pi. How long, if I pick this little point here, how long is it before I get to the same point on the graph again? Pi length, 180 degrees. It takes 180 degrees to get back to the same point. Okay? So tan has a length of pi, but we don't use the word length. So if I go back to this here, we had these options, which I hope you looked at before. I asked you, I went way too long, I'm sorry. So we did progressive mode, we did radians, we looked at the range of the produced function, 1 and minus 1. We looked at infinity for tan, for the range. How does it correlate to the quadrants in the unit circle? Hopefully I went through that with you. And here's the thing that I want to focus on for the final part of the lesson. Trig functions belong to a special group of functions called periodic functions. And that means that it repeats after a certain length of the domain. Now, that certain length of the domain is called the period of the function. Okay, so if I said to you, what's the period of sine? The answer is 2 pi, or 360 degrees. What's the period of cosine? 2 pi, or 360 degrees. I love this chanting that we're all doing because we're all on board. What is the, what's the period of sine? 2 pi. Or 360 degrees. However, the period of cosine is, I can hear all voices on this video, we'll keep going. The period of cosine is
2 pi.
Yeah, or
60 degrees.
sine though has a period of
2 pi.
whereas cosine has a period of
2 pi.
and both of those values are just
360 degrees.
honestly. This is the choir of hard knocks here. Tan has a different period. Tan's period is it repeats after pi or 100. Someone just said 80, I'm sure of it. 180 degrees. Okay, so sine, cosine have a period of 2 pi. Sine and tan is a period of pi. Now, what we've looked at here is the period of a base graph. Sine, cosine, and tan, they are all base graphs. Okay? We can apply the empty sound in the video is me waiting for people to be quiet down the back. That's better. We can apply transformations to each of the 3 base functions in order to create new functions, and they will affect the domain and range. They will affect the period. Okay, we've only got 1 minute left. I got you to fire up Desmos, so let's just have a quick look, but we'll look at it properly next lesson. So in Desmos, let's just start off with y equals sine x. Don't worry about what it looks like. It's just using our kind of standard 1, 2, 3, 4 axes. We want to change those to pies and stuff later on. But we'll just for the last minute, we'll do this. So we know that transformations are dilations, reflections. The quietness in the video again is me waiting for people down the back again. Beautiful. Maybe if you're not ready to do it by yourself, maybe just watch. So y equals sine x is this beautiful sinusoidal wave. We know that transformations are dilations, reflections, and translations. In Maths Methods Foundation, because it actually makes it much more complex, we, believe it or not, don't look at translations of trig functions, but we do look at dilations. There are input dilations and output dilations, and there are reflections as well. So if we put a value before sine of x and see what happens to the function. I'll do it now as well. I'll pick 12. Okay, that was a bit ambitious. I'll do 6. We can see that it still has a upper and lower boundary, but the graph has been stretched vertically. So it's now minus 6 to 6 instead of minus 1 to 1. Now do a dilation of the input. So put a value before x. I'm going to choose a fraction. You can see that my sinusoidal wave here has now been stretched out, but the range is still the same. Okay, so next week we're going to have a look at dilations and reflections and how they can create new sine graphs, cosine graphs, and tan graphs. I will leave it there for today, but before you leave,